In this episode of Fuel Talk, we're going to get into some electronics, namely a power distribution module. Power distribution modules can examine or control output of powered devices for a vehicle using a CAN bus system. We're going to develop our own using the Arduino platform. And one of the advantages of using an Arduino platform is that you get to make it do what you want it to do. And in our case, we're going to use it to control a fuel pump, monitor its voltage and current draw, but more than that, we're going to be able to predict some of its operating characteristics, namely the flow rate and fuel pressure. And we'll get into how that is accomplished. For other people coming to this channel for this project on the electronics side, this gives them the ability to make some kind of a power distribution module to control something in the vehicle and be able to control that through the CAN bus system. And we'll get into it right now. Power distribution modules come in all types of forms. A lot of them are OE, but of course the racing aftermarket has coming up with all types of different systems that can be used to integrate into your racing systems. A lot of the power modules that are settable usually have some type of a settings that you can access to change the different modes or different characteristics of the module, and some of them to control different aspects of what these systems will do. For our purposes, we're going to look into using the Arduino platform in that we can really tailor in exactly what type of characteristics we're looking at and what type of systems. Before we get too far into the weeds with this project, let's try to define what we're trying to do. Here I have a list of some of the minimum characteristics. Now, number one, ability to control the output. That may or may not necessarily be a desired action for this system. However, I do plan on putting some of the infrastructure into the system, to our next prototype, in order to get a good idea of how well we can control the output, and to also test the circuit for the input protection. And that's all part of this same circuit, and eventually we'll get to it on one of the other parts of this series. All these features can be expanded on, and that's why I wanted to talk about the next topic is mission creep. Whenever you're designing something, there's always the possibility of more and more features that want to get added in. Anytime you're designing something, something always gets added. One of the things is that we can expand the number of fuel pumps that we're taking a look at. Many aftermarket racing systems, they can include lift pumps, they can include multiple fuel pumps that are being used, as well as you can have as many as 3 pumps running back there or more. That's one way that the mission can creep for a given module. And another thing that's really important that it probably could expand to is the ability to read in external voltages, or even a pressure transducer or a temperature sensor. A lot of that can be helpful, especially a pressure transducer that gives you feedback automatically of what the pressure actually is versus what you're estimating at through its performance. And this can also allow you to have in your programming the ability to verify that do we have good fuel pump operation, or is something happening specifically to the fuel pump that would cause these types of misconnect. If with these expanded features, we can have essentially a fuel control module that it allows to be in the back of the vehicle with a tank that can monitor the entire situation of the fuel system. Not just the lift pumps, but also measuring what the actual fuel capacity is in the tank. In fact, if you had a voltage input coming into the module, it can be calibrated directly to how much fuel is inside the tank just by tapping into the fuel level sensor. In fact, with this intervention, you can have it extremely accurate in determining how much fluid actually is in there. Instead of just having a sweep from empty to full, you can have quite accurate readings to know precisely how much fuel is available. It is important to note because mission creep happens in every project that you'll ever go into. Once you start developing on these systems, every single system I've ever dealt with, there's always a situation where as you're making the part and the vision becomes more and more clear, other things become more apparent about, hey, well, while we're in here, this can do that, or this particular feature is more important, or that particular feature is more important. So a lot of times I kind of call this all mission creep, but it invariably happens. Sometimes mission creep happens while you're doing a project for a customer that suddenly, hey, you know, we've got a new idea to where you go. And a lot of that can play a role into what the final configuration is. But for our purposes here, in getting to this next prototype level, is really about trying to not concentrate on the mission creep aspects, but what are these minimum characteristics that we're wanting to get and wanting to take care of. And keeping a little bit of the mission creep in mind is that we can have some added systems later that we can add, like a data acquisition chip to see what we can get about for external voltages and so on. But in the interest in getting things going with the project, we're going to try to keep that as much on the back burner as possible. And in the future, when we get into the development stage of an actual having our own prototype PCB and securing our own component level parts, we can really get into, hey, here's additional things that we can add into the mix. Things like a header for an I2C bus. We can add in other types of headers so that we can modify the design once it's already built in order to see about expanding other functions. One of the things that's helpful in designing a system is that engineers have a dirty little secret that scientists can't stand, and that engineers will just be more than happy to say, I don't know. I don't know what this is. I don't know what that is. And we're comfortable with that. For example, we know that we can use a computer and not know how the silicone die was created, or how it was made, or how it was implemented. How did they make the microprocessor? I don't know. I'm comfortable with not knowing things. And with that trick, we can actually go in and get a better idea about how we're going to go about in creating a new design. For example, here I show, put a circle around something that you don't know. For example, we're starting this PWM project. We can put it in a circle and say, I don't need to know what's in it in order to start working on the project. And what this little trick that engineers do is that we don't need to know what's inside there. We just need to know how it's interacting with the outside world. You know, what temperatures are happening outside of it? What are the inputs? What are the outputs? Or what does it look like from the outside of what's going on inside there? And from there we can take an approach to go further into the circle and going, how are some of the ways that we can measure the current draw through the system? How are some of the ways that we can read the voltage? And also, what is it that we can do in order to control the device, to turn the device on and off? And what would that look like? And as we get further and further into the design, we can bring our vision further and further in defining all the details into knowing how we can construct this. Here are a couple examples of some fuel pumps, and it can just show a variety of what kind of systems we're talking about. For example, this one over the right, this is a typical OE pump, in-tank fuel pump, and maybe it supports a few hundred horsepower. And this one will support quite a bit more. This one's an electronic fuel pump, and what it has is a speed control capability. And over here is this one that supports even more horsepower. This one can support probably up to 2,500 horsepower easily, but it also has a speed control capability. But one of the things that all three of these have in common is that they take electrical power in and use that power to produce the flow power that is supplying the fuel system. And when we look at this fuel pump in particular, it came with a flow diagram. This is a sheet that was produced when the fuel pump was produced, and what it shows is the flow rate versus pressure, and also shows a current draw versus pressure. Also has two different lines. This was in a reduced speed mode, the dashed line. As you can see, it brings the current draw much further down if the flow demand is not required. One of the things that I'm showing you with this is showing you how straight these lines are. They're generally considered pretty linear, whether we're looking at the current draw performance or the flow performance. There's some variation to it, but let's take this data and make a general example of what we're talking about when we're relating the input voltage and current draw versus the output pressure and flow rate. Let's take a look at the data. This is an example of like the data that we have here on the sheet. This is showing the performance graph, and we have flow versus pressure as well as the amount of current draw versus pressure. And from these two values, we can put those together. Like such as in this graph, this represents the pressure and the flow rate as a function of the current draw, once you get that straight. Now, as we talked about being in a linear range, you can see that these are also linear showing, and we can represent any function that's linear as the following, and such that if we put in a value for x, we can get a value for y. We can go back to our graph and use this, and what this does is enable us to come up with some equations to represent the two different phenomena that we're looking at. And in this case, since we're looking at only 13.5 volts, we can represent the data as 4 different constants. Now this becomes a lot more complicated as we get through it, because in the next episode we're going to cover showing how do we deal with when it's not 13.5 volts. What if it's 9 volts, or what if it's as high as 15? Obviously the performance of the pump will change, but if we know what the performance is at those different values, we can apply some other mathematics that will allow us to derive new equations such that we can find values for these derived equations based on those different values, and that way we can get an idea of what the flow rate and the pressure is based on the current draw. And for the outro, I wanted to show this a little bit. It's the world's largest vehicle fuel system. It uses kerosene, good fuel to have to work with, but one of its caveats is that it is more about its power than about its capacity. and in this case enough power to lift up a tiny building and chuck it into space in under 3 minutes. And when you're feeling a little overwhelmed, just think that it's not really rocket science, fuel systems, but maybe it is a little bit. The Saturn V.